Today we're going to be talking about the early atomic theories. Democritus came up with the idea that matter is composed of tiny particles in 460 BCE. Those tiny particles were given the name atomos, meaning uncuttable or indivisible. They thought that if you cut something in half enough times, you would be able to reach a point where you are unable to split it anymore. The atomic theory we have today is a result of the research and studies done by many different individuals who shared their insights and thoughts. Democritus's ideas were based on intuition and reason, but he never did any experiments to prove his hypothesis. And for the next 20 years, no convincing evidence was available to support the existence of atoms until new tools were developed to experiment with matter, and our understanding of the structure of matter increased. During the 1700s, French chemist Antoine Lavoisier proposed the law of conservation and mass, which states that even if matter changes shape or form, its mass stays the same. He and other scientists used experiments to gather the first accurate quantitative measurements of chemical reactions, and based on the results of these experiments, John Dalton proposed the first modern atomic theory, that elements consist of atoms that cannot be created, destroyed, and divided, and also that atoms of the same element have the identical size, mass, and other properties. English physicist J.J. Thomson was the first to provide evidence for the electron. In 1870s, scientists began studying the composition of certain things using discharge tubes, which is basically a gas-filled tube with electrodes in each end that emits light when an electrical current passes through them. Because the light was originally produced by a negative electrode or cathode, it was called a cathode ray tube. English physicist J.J. Thomson studied cathode ray tubes even farther by measuring how much heat the cathode rays generated, how much they could be bent by magnets, and other things, and with this he was able to estimate the mass of the rays. The mass of the rays was about 1,000 times lighter than the mass of hydrogen, the smallest bit of matter known at the time. He concluded that the cathode rays were not rays or waves, but they were actually very light, small, negatively charged particles, which we now know as electrons. Thomson knew that the atom had a neutral charge overall, so he imagined that the negatively charged electrons were distributed randomly in a positively charged matrix. He visualized this model as a blueberry muffin. Similar to blueberries in a muffin in Thomson's plum pudding model of the atom, the electrons were shown embedded in a uniform sphere of positive charge. In 1909, a scientist named Robert Millikan conducted experiments at the University of Chicago. In his experiments, he used oil drops that were charged to find the charge of an electron. Through this experiment, he discovered that the fall of charged oil droplets due to gravity could be stopped by adjusting the voltage across two charged plates. With this, he was able to calculate the charge on the oil drop from the voltage and the mass of the oil drop. Using this value and the charge-to-mass ratio determined by Thomson, Millikan calculated the mass of the electron to be 9.11 times 10 to the power of negative 30.
1911, Rutherford designed an experiment where positively charged alpha particles are fired at a thin sheet of gold foil. His experiment also led to the discovery that the atom is mostly composed of empty space, demonstrating how the alpha particles pass either directly through the foil, reflected back, deflected in different angles, while some reflected back towards the source. He also discovered that the atom is composed of a dense, positively charged atomic structure in the center, which is the nucleus. Both the alpha particles and nucleus are positively charged, hence why some alpha particles repelled instead of directly passing through, because like charges repel each other. Rutherford later named the positive charges as protons, while James Chadwick worked with Rutherford to determine the masses of the nuclei of different elements. In these experiments, they found that the masses of the nuclei were not the same as the sum of the masses of the protons. Chadwick also concluded that a nucleus must contain not only positively charged protons, but also neutral, uncharged particles called neutrons. In 1900, German physicist Max Planck was studying the spectra of the radiant energy emitted by solid bodies heated to incandescence. When solid is heated to high temperatures, it begins to glow. First red, then white, and then blue. The intensity of the light of different colors can be shown in a graph to produce a curved line. Now back then, physicists speculated that the energy curve would continue to go up as temperature increased, since they thought that matter could absorb or emit any quantity of energy. However, Planck's experiments showed that the curve reaches a certain peak and then decreases, which also correlates to the temperature and moves towards higher light frequencies as the object becomes hotter. Planck accounted for the unexpected results of his experiment by postulating that matter can gain or lose energy. Now, Planck was aware that radiation was emitted as electrons moved back and forth, and hypothesized that the energies from the oscillating atoms in the heated object are multiples of a small quantity of energy. A burst or packet of energy is known as a quantum of energy.
The Bohr model of an atom. Niels Bohr was a Danish physicist who studied under J.J. Thomson at Cambridge University in the United Kingdom. An early model of the atom was developed in 1913 by Danish scientist Niels Bohr. The Bohr model shows the atom as a central nucleus containing protons and neutrons, with the electrons in circular orbitals at specific distances from the nucleus. He knew that this model had to account for experimental evidence provided by spectroscopy, which is that electrons could have only particular discrete energy levels. Bohr proposed that electrons could only move in specific orbits around the nucleus. He assigned each orbit a specific energy level and postulated that the energy level of an orbit increases with its distance from the nucleus. When an electron gained more energy when it was excited, it could move into an orbit farther from the nucleus.
The octet rule is a rule stating that atoms lose, gain, or share electrons in order to have a full valence shell of 8 electrons. These orbits form electron shells or energy levels, which are a way of visualizing the number of electrons in the various shells. These energy levels are designated by a number and the symbol n. For example, the 1n shell represents the first energy level located closest to the nucleus.
To help you envision how the orbits in Bohr's model relate to the line spectrum of the hydrogen atom, imagine a ball sitting on a staircase. This is the staircase example. Since the ball can only be positioned on a stair, it can only ever be found at specific distances from the ground. Applying Bohr's theory to this analogy, the higher up the staircase the ball is, the more potential energy it has. If the ball moves up the staircase, that is to a higher energy level, it gains potential energy. But if it moves down the staircase, that is to a lower energy level, it loses potential energy. Theory to this analogy, the higher up the staircase the ball is, the more potential energy it has. If the ball moves up the staircase, that is to a higher energy level, it gains potential energy. But if it moves down the staircase, that is to a lower energy level, it loses potential energy.